Hello APChem, this is Mr. Coker. I'll be doing the first half of Chapter 7 in this video, so 7.1 through 7.6. This is a chapter where we begin talking about the structure of the electron cloud in the atom. As you should know from Chem 1, the atom is a nucleus with protons and neutrons surrounded by an electron cloud. Understanding the layers of that electron cloud and the various ways in which that cloud can interact with other atoms is crucial to understanding chemical bonding and properties of atoms. And so we're going to talk about what we know about the atom's electron cloud and how we know it. The main probe that we use for studying the electron cloud is light. Light can also be called electromagnetic radiation. So that would be electric and magnetic fields traveling through space while oscillating. So the picture in the upper left down below is an example of how the electromagnetic field works. You're always going to have the magnetic field at a right angle to the electric field, and so you have simultaneous oscillations of both fields at right angles to each other, and those oscillations travel through space at the speed of light. The distance between the crests and troughs, so crest to crest or trough to trough, is called the wavelength, and it uses the symbol lambda, which looks like an upside down Y. That can be measured in meters, or sometimes it's measured in nanometers. It's important that you keep track of which one you're being given in a problem and that you make the proper conversions so the units work in your problem. I would say units are crucial. The mathematical formulas aren't that complicated in this chapter. Probably easier than the gas law formulas, but the units are very critical. Visible electromagnetic radiation from violet to red, Roy G. Biv, spans a range of about 400 nanometers to about 700 nanometers. You can see the visible spectrum down below. Notice the visible spectrum is only a small fraction of all the electromagnetic waves. They can be very long waves, such as AM radio waves are like 100 meters. They can be very small waves, very small wavelength waves, such as gamma rays. But the ones between about 400 and 700 nanometers are the ones that our eyes can pick up on. The formula for wavelength and frequency, we should talk about frequency first. Frequency is the symbol nu. I believe in Chem 1 we call it F, but the APChem uses the symbol nu. It looks a little bit like an italics V. There is a V for velocity in this chapter, so be very careful to check whether the symbol you're looking at is velocity or frequency. But frequency is the Greek letter nu. Frequency is measured in waves, cycles per second, or 1/seconds, or hertz. And C equals lambda nu shows us that the wavelength and frequency are inversely related and that they multiply to give us the speed of light, c. If you're looking for a number for c, 3.00 times 10 to the 8th meters per second is the speed of light, c. Interactive example 7.1 is practice using that equation. So now if we look at the nature of matter and along with it the nature of energy, we find that both energy and matter can be described both as particles and as waves. Up until the early 1900s, physicists would have told you that light was a wave, and it is. but the work by Max Planck on the trying to explain the ultraviolet catastrophe showed that light can also be considered a particle. And that particle is called a photon, and it has an energy equal to Planck's constant h, which is 6.626 times 10 to the minus 34 joule seconds, multiplied by the frequency. So in other words, high frequency light has high energy photons, and that would mean that high energy photons have a low wavelength because frequency and wavelength are inversely related. Einstein quickly picked up on Max Planck's work on the particle nature of energy and used his idea to explain the photoelectric effect. The photoelectric effect deals with light shining on metal surfaces and causing electrons on the surface of the metal to gain enough energy to escape and be emitted. It was found that if the frequency of the light was too low, in other words, it was below a certain threshold frequency, if it was below a certain value of frequency, that no matter how bright the light or how highly intense the light was, no electrons would be emitted. And that's because the difference in energy between the electron in the highest level of the metal and the electron out of the metal was too great for the photons of light to change its energy enough to get it out of the atom. However, if you get above that threshold frequency, you do emit electrons because the photons have enough energy to change the energy of the electrons from being in the atom to being out of the atom. In fact, if you shine the light with that threshold frequency or higher, if you shine it brighter, you get more electrons being emitted. Einstein also showed that the kinetic energy of the electrons being emitted is larger when the frequency is greater, and that's because any leftover energy from getting out of the atom it allows the electron to have more kinetic energy. So an analogy for that would be, let's say your mom gives you $10 for lunch, and then when your mom washes your jeans, she finds $3 left in your pocket. She would know that you spent $7 on lunch because she knows the energy of the photon that was used, and she knows how much kinetic energy is left over after some of that energy is used to get the electron out of the atom. So that would be the analogy for that. Louis de Broglie in the mid 1920s suggested that if photons could be particles of something that we normally think of as a wave, light as a wave and as a particle, maybe electrons might display that wave-particle duality as well. And he calculated the formula that the wavelength would equal Planck's constant over the mass times the velocity. So that's down in the lower right-hand corner. So the idea of electrons having wave properties was tested in the 1930s by Davison and Germer at Bell Labs, and they showed that electrons passing through a crystal do have diffraction patterns, and diffraction is a property you only see with waves, and so it proved that the electron does have wave properties. Interactive examples 7.2 and 7.3 can help you with the formula E equals h times nu, which if you do a substitution can also be written as E equals hc over lambda. Make sure you try these example problems because the units for these take a lot of practice, making sure that you're getting your units properly converted so that when you plug in your numbers, you're getting the proper answers. 7.3, we look at the atomic spectrum of hydrogen. As you remember from Chem 1, looking through the spectroscope like the one at the bottom of this slide, You do see lines. We have the hydrogen line spectrum, which shows 4 visible lines. Hydrogen also has some infrared and some violet lines. The infrared lines were called the Paschen series. The visible lines were called the Balmer series. And the ultraviolet lines are called the Lyman series. And that's after the scientists that figured out the mathematical formulas that will allow you to calculate those particular lines. The hydrogen line spectrum tells us that hydrogen has very specific energy levels, and that when electrons are being lowered or relaxed in energy from higher levels to lower levels, that they emit certain photons of certain wavelengths based on the energy of the difference between those energy levels. So the way this works is you have different energy levels, and if the electron is excited with heat or electricity to a higher level, when it drops to a lower level, it'll give off a predictable amount of energy. That energy corresponds to a certain wavelength of light, which corresponds to a certain color. And so it appears that there are 4 possible transitions for hydrogen that will give us colors in the visible part of the spectrum. There are more than just 4 transitions that can occur between energy levels in hydrogen, but there are only 4 that give us visible colors. The Bohr model was actually able to explain the hydrogen spectrum. Bohr in 1913, right after Rutherford finds the nucleus of the atom, Bohr proposes the quantum model for the hydrogen atom. He quantizes the electron energy levels and says that electrons only move about the nucleus in certain allowed circular orbits. So his model is sometimes called the planetary model. But he uses some physics and the idea of quantization of energy for the electron energy levels to explain the various electron energy levels that are allowable for hydrogen. And if you take that idea and look at the energy levels that he calculated, the energy levels have energies equal to negative 2.178 times 10 to the minus 18 joules times z squared over n squared. And so that is the formula down below in the upper right of the pictures. The energy being negative simply means that the electrons have less energy when they are in the atom and more energy when they are out of the atom. So in other words, you have to give them energy to bump them out of the atom. Generally, just like kind of with the Celsius scale, we set 0 to be the freezing point of water. We set 0 for the energy scale for electrons to be an electron that is not in an atom. So when electrons are removed from the atom, their energies, their potential energies are 0. They might have kinetic energy, but they have no potential energy. As they are absorbed by atoms, their energy lowers. So if 0 is out of the atom, lower than that would have to be a negative number. So it may be hard for you to think of potential energy as being negative. Normally we think of potential energy for gravity as if it's in its lowest possible position, it's 0, and then if it's up on some kind of tabletop or up a ladder or something, that the potential energy is positive. So maybe a way to think about this would be, what if you dug a hole? Then if the ball or whatever object has potential energy falls into the hole, then if ground is 0, then down in the hole would be negative. So we sometimes call it a potential energy well, as if we've dug a hole in the ground, and the electron has lower energy in the well than it does at ground level, and or at being out of the atom, where it would be 0. So this formula, E equals negative 2.178 times 10 minus 18 joules times z squared over n squared, The Z stands for the nuclear charge, which for hydrogen would be 1. But this equation could be used on anything with just one electron. So an helium plus 1 ion, Z would be 2. Or a lithium plus 2 ion, Z would be 3. It will not work for atoms or ions that have more than 2 particles. They have to just have a nucleus and 1 electron. N is the energy level of the electron, so N would equal 1 for the first energy level and 2 for the second and 3 for the third. So now that we have a formula like this, we can plug in Z for hydrogen equal to 1 and calculate that the energy for the first energy level is negative 2.18 times 10 minus 18 joules. For the second energy level, it's negative 5.45 times 10 to the minus 18 joules. And for the third energy level, it's negative 2.42 times 10 to the minus 19 joules, as seen below. So then if I want to know what is the energy of a photon if I move from level 3 to level 1, all I have to do is find the difference between negative 2.42 times 10 minus 19 joules and negative 2.18 times 10 minus 18 joules. Subtracting those two energies would give me the difference in energy between the two levels, which is the energy of the photon emitted when you drop from the high level to the low level. Once you know the energy of the photon, you can find its wavelength using E equals hc over lambda, or you can find its frequency using E equals h nu. So that's basically how you use the Bohr formula for the electron in the hydrogen atom. The Bohr model stuck around for about a dozen years. In the mid-20s, Werner Heisenberg states his uncertainty principle, that it is impossible to measure the position and momentum of such small particles as electrons in atoms. So as a result, he sort of says that the Bohr model would not be testable because you would have to be able to observe the electron orbiting the nucleus to be able to test it out. So Heisenberg is considered one of the scientists that led us to the next model of the atom. De Broglie, of course, with his idea of electron as waves, as another one. But the main scientist who is credited with the quantum mechanical model of the atom, or the cloud model of the atom, is Erwin Schrodinger. Schrodinger does some differential equations that describe the electron as a wave within the atom. So if you think about how sound waves resonate in a pipe, in a similar way, electron waves can form standing waves or resonating waves in an atom. And by doing the mathematics of waves, you can actually calculate the regions of the atom that will have low and high probability of finding the electron at those positions. And so it becomes a mathematical model. And with this mathematical model, you can figure out what distances from the nucleus are going to have the highest density of electron cloud, or the highest probability of finding the electron at a particular location. So we see that you can make graphs of the radial probability density and other kinds of mathematical functions to describe the position of the electron as a cloud. Now the cloud actually just gets thinner the farther you get from the nucleus. So generally what we do to talk about the size of the cloud is we simply figure out where 90% of the cloud is enclosed, and that particular structure, the 90% probability region, is our electron cloud. So that can be an entire cloud for an atom, or it can be a portion of a cloud, such as an energy level or a shell, or even an orbital like a 1s or a 2s or a 2p. The mathematical formula, at least one version of the mathematical formula that Schrodinger developed, is shown in the lower left. So if anybody wants to try to solve that, you're welcome to try. The Schrodinger equation has multiple solutions for a given atom. So those solutions can be described by a set of 4 quantum numbers. The quantum numbers, when you look at what values they're allowed to have, can help us figure out how many energy levels and sublevels and orbitals and electrons can actually occupy the various parts of the electron cloud. So just briefly, the principal quantum number, or the first quantum number, is called the N quantum number. It's given the letter designation N, and it deals with the energy level of the electron, which is related to the size of the cloud. When n equals 1, you have the first energy level, and the first energy level is closer to the nucleus, and so that is a smaller cloud. N equals 2 is the second energy level, and it is sort of a shell surrounding the first energy level, and so forth, 3, 4, 5, 6, 7. The energy levels simply build like layers of an onion. Ogres have layers and onions have layers, so those energy levels build outward from the middle, 1, 2, 3, 4, 5. Now within those energy levels we have sublevels, and those are the shapes of the clouds. L is the sublevel quantum number, or the angular momentum quantum number, and L can have values of 0 or 1, but for a given energy level n, L can only go as high as n minus 1. So for example, for the first energy level, L only equals 0. For the second energy level, L equals 0 or 1. For the third energy level, it equals 0, 1, or 2. So any particular energy level is going to have the same number of sublevels as its energy level number. So the fourth energy level has 4 sublevels. The fifth energy level has 5 sublevels. And those are given the values 0, 1, 2, 3. You may have also remembered from Chem 1 that when L equals 0, we call it an S sublevel. When L equals 1, we have the P sublevel. When L equals 2, we have the D sublevel. When L equals 3, we have the F sublevel. S, P, D, F actually come from the days of spectra, studying the line spectrum of an element, and they are actually the first letters in the words sharp, principal, diffuse, and fundamental, which were the words that were used to describe the various lines in the line spectra of atoms. And so we shortened the sharp, principal, diffuse, and fundamental down to S, P, D, F. The third quantum number, m subscript L, or m sub L, is the magnetic quantum number. It deals with the orientation of the clouds. So the m sub L quantum number can be any number between negative L and positive L. So if you recall, for the S sublevel, L equals 0. So there's only one orientation, 0, for the S or L equals 0 sublevel. The P sublevel, where L equals 1, can have orientations designated negative 1, 0, and 1. And so those actually correspond to the px, the py, and the pz, the 3 different orientations of the p orbitals. For the d orbitals, L equals 2. So you have negative 2, negative 1, 0, 1, and 2. And so that explains why there are 5 orbitals in the d sublevel. The f sublevel has 7, negative 3, negative 2, negative 1, 0, 1, 2, and 3. Now the fourth quantum number is nothing to do with the cloud. It has to do with the spin of the electron in the cloud. It turns out that each set of 3 quantum numbers, n, l, and m sub l, can have one of 2 possible spins for the electrons, and those are plus 1/2 and minus 1/2. So what that allows us to calculate is that there will be 2 electrons per orbital, and varying numbers of orbitals per sublevel, and also varying numbers of sublevels per energy level. But the chart down below takes you up through the first 3 energy levels. So we have the 1s, where n equals 1, So L equals 0, so M sub L equals 0, so the spin equals plus or minus 1/2. So that's 2 electrons in the first energy level. And the first energy level only has a 1s sublevel. The second energy level, 2, has a 2s and a 2p sublevel. So N can equal 2, but L could equal 0 for 2s or 1 for 2p. If L equals 0, you have only the 0 magnetic quantum number possible. And you only have plus or minus 1/2 for the spins. So the 2s holds 2 electrons. For the 2p, N equals 2 and L can equal 1. So then the magnetic quantum number can be -1, 0, or +1, or 2px, 2py, and 2pz. Each one of those 2p orbitals can hold 2 electrons, one with a plus 1/2 and one with a minus 1/2 spin. So that means if you have 3 orientations, you can have 6 electrons. So then that totals up to 2 electrons in the 2s and 6 in the 2p for a total of 8 electrons in the second energy level. And you can also kind of work that out for yourself for the 3s, the 3p, and the 3d. Just study that table and you'll see that 18 electrons can fit in the third energy level. So that is how quantum numbers work for describing the various energy levels, sublevels, orbitals, and spins of electrons in the atoms. Thank you very much.